Hi, I'm Abraham Vinod. In this video, I will summarize and show hardware demonstrations from a recent work on spatial monitoring using heterogeneous robots. The title of the accompanying paper is Data-Driven Spatial Classification Using Multi-Arm Bandits for Monitoring with Energy-Constrained Mobile Robots. In this work, we want to classify the regions of a search environment into interesting and uninteresting regions as quickly as possible. We wish to solve the problem using noisy data collected by a team of mobile sensors and mobile charging stations. We also want the team of robots to satisfy a variety of physical constraints, including those arising from dynamics, limited battery, and collision avoidance requirements. We propose a bi-level iterative algorithm that combines recent advances in multi-arm bandit literature and optimization-based planning. Our approach is illustrated in the figure on the right. At each iteration, we generate data-driven confidence bounds and use a bandit-based high-level planner to choose the cells to visit next. We then use an optimization-based low-level planner to design trajectory for the team that satisfies the physical constraints. Based on the new data collected, we update the confidence bounds as well as the sets of classified cells. The low-level planner designs paths as a collection of sensing cycles. Here, each sensing cycle is such that the sensors always start and end on a station and respect the physical constraints on the team. We also provide several theoretical guarantees for the method in the paper, including anytime property, as well as an upper bound on the task completion time. We now briefly discuss the setup used for the hardware experiments. The figure on the left provides an overview of the implementation details. In our hardware experiments, we use Crazyfly drones as mobile sensors and Turtlebots as ground stations. We used a combination of softwares, including Crazy Swarm 2, OptiTrack motion capture software, and custom ROS2 packages to control the robots. We used OpenCV and onboard cameras on the drones to implement vision-based sensors for monitoring. The figure on the right shows the testing environment. We used a team comprised of 4 drones and 2 ground robots in a 6x6 grid environment representing a search and rescue application. The setup includes 11 obstacles, which are the colored triangular pyramids, 2 roads, which are delimited by triangular tiles within which the stations are constrained to remain, and 4 interesting regions that contain the search objective, the green tiles. The algorithm knows the location of the roads and the obstacles. However, the algorithm must deploy the team to collect data and correctly classify the 14 remaining cells as interesting or uninteresting as quickly as possible. We now show the first hardware experiment. On the top left, we will show the images collected by the drones or indicate that they are either in transit or being charged as shown now. On the top right, we will show the percentage of cells classified as our approach progresses. We show the count of classified cells in the legend. Here, epoch denotes the time in a slower time scale as used by the high-level bandit based planner. Note that each epoch may have multiple sensing cycles. On the bottom right, we show the cell labels and update it at each epoch. On the bottom left, we show the video from the physical experiment. As seen from the video, our algorithm coordinates the team of drones and ground robots to visit all the cells and correctly classify the cells as interesting and uninteresting. We also note that the paths designed by our algorithm are such that all physical constraints on the robots were met. Our approach requires 5 epochs and 6 sensing cycles to complete the task. To validate our approach against noisy sensors, we also performed an additional experiment where we used an intentionally degraded image-based classifier. On the left, we show the video of the physical experiment with the unmodified sensor. This is same as the experiment video shown previously. On the right, we show the results from the physical experiment where the sensors are now degraded by adding a 5% classification noise. As expected, using a degraded sensor forces our algorithm to take more time to complete the task. However, it still completes the spatial classification task within just two additional sensing cycles compared to the unmodified classifier scenario. See the accompanying paper for additional detailed simulation-based analysis where we study the effect of agility, team sizes, and other parameters of the algorithm on the performance.